2010 released FRQ number 2. This is a table problem. So we have a zoo-sponsored one-day contest to name a baby new elephant. Cool, elephants. Zoo visitors deposit entries in a special box between noon and 8. The number of entries in the box after noon is modeled by a differentiable function. Cool. That means we're continuous, right? Differentiable means continuous. Values of E of t in hundreds of entries at various times are shown at the box. So like at t equals 2, there's 400 entries. At t equals 5, there's 1300 entries, and so on. Use the data in the table to approximate the rate, so we're going to try to find a rate or look at a derivative, in hundreds of entries per hour at which the entries are being deposited at time 6. So I don't actually know the value at time 6, but we're going to use our data to approximate that. So for part A, we want to find basically E prime of 6, which means to find the rate of change at 6. So it's E of 7 minus E of 5 over 7 minus 5, which gives us 21 minus 13 divided by 2, which is going to give us 400 entries per hour. Alright, part B. Use a trapezoidal sum with 4 subintervals given by the table to approximate 1/8 E of t. Using correct units, explain what this means in terms of number of entries. Okay, so trapezoidal sum, it's going to be h over 2 times b1 plus b2. That's how you're going to find the area of each trapezoid. So we want to find 1/8 integral 0 to 8 E of t dt. So it's going to be 1 over 8 times, and then to find the height, you subtract these values. So I want 4 subintervals. So there's my first, second, third, and fourth. So to find my height, it's 2 minus 0, 5 minus 2, 7 minus 5, and 8 minus 7. And then these are going to be my bases. Okay, so it becomes 2 over 2, 0 plus 4, plus 3 over 2, 4 plus 13, plus 2 over 2, 13 plus 21, plus 1 over 2, 23 plus 21. And when you add all those up, you're going to get a nice 10.6875. So the integral from 0 to 8 of E of t dt is equal to 10.6875 is the average number of entries in the box between 0 and 8 hours. Alright, part C. At 8 p.m., volunteers begin to process the entries. They process the entries at a rate modeled by the function where P of t is equal to that crazy function. From 8 to 12, according to the model, how many entries had not been processed by midnight? So what this one is saying is that the ballots go in the box between 0 and 8 hours. And then after like 8 o'clock, the officials come out and they start counting them. And P of t is the rate at which they count it. Okay, so if I want to know how much have been processed, I'm going to integrate P of t. So the first thing I need to do is I have 2,300 entries, and I'm going to subtract the amount that have got counted, which is the integral of the rate at which they get counted. So then this is going to be 23 minus 16, which is 7. So there's 700 entries left at time 12. Alright, according to the model from part C, at what time were the entries being processed most quickly? Justify your answer. So when you see this most quickly, you should think of like a maximum. Okay, so what we want to do is when are the entries being processed most quickly? So this is the rate at which they're being processed. So I want to set the derivative of P equal to 0. So the derivative of P is 3t squared minus 60t plus 298, and we're going to set that equal to 0. You go ahead and just graph that on your calculator, and you get t is equal to 9.183, and t is equal to 10.816. So we have to check not only our critical values, but our endpoints. So we have t and p of t, and our t values are going to be 8, 9.183, 10.816, and 12. So you go ahead and put those in your calculator, and you get 0, 5.088, 2.911, and 8. So our entries are being processed the fastest at t equals 12, or at midnight.